So taking a look at an organolithium. So this is a carbon that's bonded to lithium. So that should be a giveaway, right? That's lithium's a metal. So we're thinking about the dipole of this. The carbon is actually going to have a negative charge. So this is actually an ionic bond. We talked a little bit about this before, right? Just because this looks like a covalent bond, right? It's not, right? You could draw it like this. That's how it's going to react. But the way they have it drawn here in sapling is like that. So you draw the 2 electrons in that bond, knowing full well those 2 electrons belong to whom? They belong to that carbon, right? Not to the lithium. They belong to the carbon. They have drawn the products for us. So if you look at what bonds are formed, what bonds are broken, you can check that out. So like I said, carbon owns the electrons, and the products are given here. So you know what bonds are formed, what bonds are broken. So some of this is just kind of getting back to used to, okay, if I have this dash, this thing here, how many hydrogens are on this right here? 3. How many hydrogens are on this carbon? 2. So the new bond that's formed is a new CH bond. Easier to see, this OH bond is broken. So that H that's on this alcohol ends up on this carbon, even though we don't draw the hydrogens in. Maybe it's harder to see when you see a negatively charged carbon here, but again, this carbon has how many hydrogens bonded to it? 2. The 2 hydrogens are still there. It's just, these are exactly the same structure, right? These structures are exactly the same, just drawn 2 different ways. One's showing this more like a covalent bond. This is showing it like a completely ionic bond, right? And we're somewhere in between. But really, the electrons are on the carbon. So we start our arrows at electrons. Lasso those. How do I know, right? One thing you always think about, how do I know something's a nucleophile or electrophile? Well, a negatively charged carbon, that's pretty reactive. That's going to be a nucleophile. And it's going to react with an alcohol, right? This whole unit's about alcohols because alcohols can act both as a nucleophile and an electrophile. So in this case, the alcohol is acting as a electrophile, as the hydrogen is the electrophile, right? Because, right, that's the most delta plus site, or the most electron deficient atom. Alcohols can also act as nucleophiles, right? The lone pairs could be nucleophilic, but, right, one of the things we need to start thinking about is, what's my most reactive nucleophile? What's my best nucleophile? What's my best electrophile? And then the other thing must be the opposite. So if you see a carbon with a negative charge, whoa, carbon is reactive and has a negative charge. That must be my nucleophile. That means the other molecule must be the electrophile. You start looking for that most delta plus site in that molecule. And here, those 2 electrons go to the oxygen. Very good. And that H, if we were to draw it out, ends up there. Good thing to do, number your carbons. What people oftentimes do is lose a carbon along the way here. Especially when you draw it as the ionic, people tend to forget or lose this carbon along the way.
So we don't have to show the lithium leaving then?
No, lithium doesn't really leave, right? The lithium, right, so if I'm taking these 2 electrons, carbon, and those electrons, carbon owns those electrons. So lithium is just along, right, that's really like this kind of bond. So lithium is just about a charge balancer, essentially, at this point. So this is like, we call these lithium salt almost, right? And same with Grignards, would be the same type of thing. If it was something like this, we could draw it like this and do a similar type of thing, right, where the electrons go, or you could draw it in more of its ionic form, where there's a negative charge there, and the plus charge on the magnesium. But I like to grab these electrons in that bond, whatever kind of bond that is, and those are the ones that react. Lithium is kind of there to balance the charge. Yep. All right, taking a look at a Grignard reagent and an organolithium, and how they're going to react with essentially water, right? It's not H2O, it's D2O, so it's heavy water. D, remember, is deuterium, so it's hydrogen with an extra neutron. But we actually use deuterium because it's not NMR active, so we can find ways to isotopically, right? We're using an isotope here to label something in an NMR experiment to So it doesn't show up. So we can find out something is or not a Grignard or that kind of stuff. So what's going to happen here is water again. So it's like an alcohol, right? We're taking advantage of the properties of an alcohol being both a nucleophile and electrophile. But in this case, both of these cases, the Grignard and the organolithium, these are nucleophiles. So that means the water or the alcohol is going to have to act as an electrophile. So where is it electrophilic at? Where is D2O electron deficient? Electron deficient on the deuterium, right? Just like a hydrogen would be. The same idea as like a hydrogen would be. Because all this difference between a deuterium and a hydrogen, we added a neutron. Neutrons are neutral. So not changing the charges. So it's the same as it would be with water. So a lot of people will say Grignards or organolithiums are really, really reactive bases. They're really like a carbanion, that's reactive. Right? They're reactive bases. That's why you can't have them around water. If you have them around water or OHs or NHs, heteroatoms, they're going to be quenched. They're going to react with that first before they react with something else. So what's the mechanism look like here? We'll draw the products. So the mechanism, I like to draw the electrons in. That carbon carries the negative charge. Those electrons are going to go there. Break the OD bond. The product will be, now there'd be a deuterium there instead of a hydrogen. Like, why you do this again, right? This is, deuterium atoms don't show up in NMR, so this is a way to do some NMR experiments. And the other byproduct would be magnesium bromide, magnesium plus charged, and then there's an OD minus, right, to balance our charge. Magnesium lost electrons, the oxygen got them, there's your balance of the charge. So you usually get an organic species, and this would be like a salt. So that should be a salt. For the other one, the organolithium, it's a very similar mechanism, little different product. The carbanion, electrons between that organic or carbon and lithium go after the D, the deuterium, just like a hydrogen, electron deficient. The OD bond breaks. The resulting product then is a D. I'm not doing a good job. Number my carbons here. Sorry. 1, 2, 3. Don't lose carbons. So now there's a deuterium on that, carbon 1. The other byproduct, I have lithium plus and OD minus. That's another salt. Balance of charge. So in the question, I think in sampling, it doesn't ask for that, but I just want you guys to see, right? We don't lose atoms. So I'm already conscious of like losing atoms. So be careful what the instructions ask for in a question, but this is the whole complete picture. I want you to see that. So we've been talking about Grignard and Grignard reagents, carbanions, and organolithiums, things with a negatively charged carbon. So now let's take a step back and think about what is a feasible Grignard reagent, right? Because we want a Grignard reagent or organolithium or carbanion to react with something else. We don't know necessarily, or where are situations where it is compatible, right? When does it work? So Grignards, remember, are right a carbon with a negative charge. So super reactive carbon, like a carbanion. So what is that going to react with? That is going to react with, right, that's a nucleophile, so it's going to react with what? Electrophiles, right? So it's a carbanion, so a negatively charged carbanion. It's going to react with electrophiles. So in a Grignard reagent, you can't have any electrophiles. No electrophiles on a Grignard, right? It won't work. Right? If there's an electrophile in the Grignard, it's just going to react with itself. Or you're never going to make it in the first place because it ain't going to work. Also, no polar, what kind of solvents? Protic solvents. Remember what protic solvents are? That's that OH, NH, SH, pH, any of those kind of solvents don't work. with Grignards, right? Because that's a really good electrophile. The OH, right? That's a polar bond of hydrogens. Those are the two things we cannot have if we want to have a Grignard. We can't have electrophiles in the Grignard, right? Because we want the Grignard to react with the other electrophile, the other thing we're at. Unless you want to do a Grignard, right, intramolecularly, and you don't want polar aprotic solvents. So you can't have OHs or NHs, either solvent or on your Grignard. So it could be a classic example of something that would not work. So let's think of let's think of, could I ever have this? Would this Grignard work? Why or why not? So it's carbanion. So what we're looking for electrophiles. Is there an electrophile in this molecule? Is there any place in this molecule where it's electron deficient? Carbon attaches to bromine. So this won't work, right? I don't want to have, right, no electrophiles on my Grignard. The carbon attached to bromine, that's a great electrophile, right? Bromine's electronegative, point away electron density. It's large, that's a long bond, not a lot of orbital overlap. This won't work. This reagent won't work. No electrophiles in the Grignard. What about another example?
So would that make it an unfeasible?
An unfeasible Grignard, right? That would be unfeasible. Unfeasible. We will not be able to do that. What about this one? Unfeasible. Why? Because that's carboxylic acid, right? Man, Grignards are carbanion. What do you think a carbanion is going to do with acid? Whoa. Right? Negatively charged carbon and some carboxylic acid, that's going to react. Really, this ain't going to happen. This molecule can't exist. So it's unfeasible to make this. You won't be able to make this. Because the Grignard's just going to react with itself way too fast. So unfeasible Grignard reagents are those with electrophiles on the Grignard. They have polar protic parts, OHs, NHs, pHs, SHs. Two more examples. So here we have a carbonyl, a ketone carbonyl, or acetyl bond O. This is also unfeasible because, again, the carbon of the carbonyl group, ketones, esters, aldehydes, it's electrophilic, right? It's bonded to an oxygen, double bond to an oxygen. That's going to make this delta plus. So this is unfeasible. Now we got an epoxide. Well, again, carbon bonded to oxygen. It's going to be a polar bond. That's going to be both these are delta plus sites. It's also in a 3-membered ring. There's some angle strain, right? These are sp3 hybridized, and triangles don't have 109.5 degree bond angles usually. At least not both of them couldn't be that. So it's going to be strained. So this is also unfeasible, right? Then electrophiles. So this is a good review of electrophiles. Carbons bonded to halogens, all the acids, OHs, NHs, carboxylic acids, epoxides. Now the new one we're looking at are carbonyls, acetyl bondos. So we're using lithium aluminum hydride, but instead of hydride, we're using deuteriums here instead of H's. So the first thing we're reacting it here with a ester, so it's doubly complex. This is a little different than a ketone or aldehyde. So let's first look at lithium aluminum hydride and what that structure of that is. So lithium, right, basically forms ionic bonds. You should kind of know that already. Lithium forms ionic bonds. So this Al(D4) has a negative charge. The question is, where is that negative charge? So if you remember where aluminum is at in the periodic table, where is it at? It's in the third column, right? Third row, third column, not row, third column. So it's how many valence electrons? It's right below boron. So it has 3 valence electrons, so it forms 3 bonds as neutral. But when you have 3 bonds, that adds up to how many electrons being surrounded by? 6. And of course, the octet rule is 8, not 6. So aluminum, when it has 3 bonds, it's neutral. But now if it has 4 bonds, it actually has a negative charge. Because it has more electrons than it normally does. It has a negative charge. But this is one of those cases where that Lewis dot structure is going to lie to us. So just because the aluminum has a negative charge, aluminum is still a metal. And these, we call this lithium aluminum hydride. Hydride, or in this case, deuteride, I guess we'd say. Hydride is an H minus. So in this case, this is a D minus. So even though the negative charge is on the aluminum, the electron density is where? It's on the deuteriums. The electron density is actually on the deuteriums. Okay? So this is my nucleophile, right? H minus, or in this case, a D minus. That's pretty electron dense, right? And that's my nucleophile. Where on an ester is it electrophilic? Where is an ester electron deficient? The C of the carbonyl, the carbon of the carbonyl group. That's my electrophile. Over and over and over. Whenever we have a carbonyl, right? The C double bond O's, different types of carbonyls. That carbon of the carbonyl is the electrophile. Unless it's a carboxylic acid, which of course is an acid. Carboxylic acid. So we've decided this is the electrophile. That's my nucleophile. So let's have our nucleophile attack our electrophile. So it's sp2 hybridized. The nucleophile is going to attack the deuterium. The 2 electrons there. Pi bond breaks. Kick those electrons up. We went from sp2 now to sp3. Oh my. So this first step is going to look like this. Balance my charge. Okay. So we have a tetrahedral intermediate. Now what you need to do though here is a little different. You look at your sp3 hybridized carbon tetrahedral intermediate, you say what's attached to it? And you say, is anything on here a good leaving group? Would anything be stable if it got kicked off? Is there anything, if I reform the pi bond, is there anything I could lose that would be stable with a negative charge essentially? The oxygen would, right? The oxygen would. So the electrons come back down and we kick that off. So we reform the pi bond. We remake a carbonyl. Now, it was an ester, and now what type of carbonyl is this? What type of carbonyl is that? I mean, it's like a, instead of D, if it was an H, what would you call that? It's an aldehyde. It's like an aldehyde, right? Well, aldehydes are pretty reactive, aren't they? Actually, aldehydes are they're pretty reactive. And notice lithium aluminum hydride has how many Ds? How many Ds did it have? 4. So it's going to keep reacting. It's going to keep reacting. And so eventually you don't need to draw this. You can just draw it as D minus. So what's going to happen? Another D minus, since you have, right, with every one of these, you have 4 hydrides. So this is a 1-to-4 ratio. You have actually extra here. You see that? To get this to an alcohol, I need to add 2 Ds, but I already have 2 extras. So if you're thinking about this like in an actual lab setting, you could do for every one of these, I could react two total of these. D minus attacks, kicks up. So rearrange a little bit here. We have another O minus. We went from, right, sp2 hybridized, carbon of the carbonyl, went to a tetrahedral intermediate again. Now it's sp3 hybridized. The original D is still there. We've added another D. Once you have a tetrahedral intermediate, you look and say, is there any good leaving groups? Is there anything I can kick off that would be stable with a negative charge? Would hydrogen be stable with a negative charge? Not normally, right? Here it is just because it's bonded to aluminum. But normally this is kind of stuck. So hydrogens and carbons won't come off, right? Because C minus and H minus are really reactive. So it's going to stay there. And once you're kind of stuck here at this, then you go to step 2. So that was all step 1. Now we're going to step 2. And step 2 was with H+. Well, H+ is a really good electrophile acid. So our O is going to react with that. And the resulting product then is a primary alcohol. But in this case, you've added 2 deuteriums. So esters, when they react with lithium aluminum hydride, are turned into primary alcohols.
What about the second product? Would the
You wouldn't isolate this. This is just going to keep reacting. The aldehyde is going to keep reacting super fast. So when I had the minus charge, the lithium was along for the ride all the way too, to balance the charge. So another side product, or the other product, of course, is your O minus here, which is also along from your original piece that got kicked out, your original leaving group. That's also going to get protonated with the H+. So when they show H+ like that, they usually mean it's in an excess, because they're essentially stopping the reaction. You're going to add a heteroatom H+ or water, and it's going to stop the reaction, but you add an excess of this. So the same thing happens. And the other product you'd get then is that alcohol ethanol.